Hi everyone. So we are working on a project, super resolution using GANs as a part of our deep learning course EE599. My team, Kartik Lakhotia, me, and Srivathsan Sundaresan. So let's dive right in. So what are GANs? GANs are generative adversarial networks. So one of the most popular examples used to explain GANs is that of the counterfeiter and the police. So a counterfeiter tries to pass off fake currency to the police as real currency, and the uh, police tries to discriminate between fake currency and real currency. So here in the generative adversarial network, the counterfeiter is played by the generator, and the police is the discriminator. So why GANs? So GANs has become a very hot area of research in the last few years, and a lot of people are still playing around and trying to figure out what applications GANs are best suited for and what all they can do. And as Jan LeCun said, generative adversarial networks is one of the most interesting ideas in the last 10 years in deep learning. Coming to the project we are working on, that's on super resolution. So super resolution is basically the task of converting a low resolution image into a high resolution image. So the way in which a low resolution image differs from a high resolution image is that the number of pixels packed into an area is lesser in a low resolution image as compared to a high resolution image.
So let's see some of the previous work on super resolution. So initially in the 1980s and the 1990s, people used interpolation techniques for upsampling like bilinear, nearest neighbor and bicubic interpolations. Then later in 2010s when deep learning took over, CNNs turned out to be a very good alternative compared to the interpolation techniques that were used in the past. Then people wanted to use deeper networks, so SR ResNets came into picture. So ResNets is just it's a deep learning architecture which is used to make uh, the network even more deeper. So here we see that SR ResNets were performing better than the convolution neural networks. Then lastly we come to our topic, SR GANs. SR GANs stand out from the other three techniques that were used in the past because they're able to produce more realistic images compared to the ones in the past. So yeah, these are just some of the examples for the techniques that I mentioned in the previous slide. Let's go into SR GANs. So here, like actually in a typical generator, in a traditional generator, we give random noise as an input, but in this case, to give the generator hits that, we give a low resolution image as an input, which then gives out a super resolution image, which then goes into the discriminator, and then the discriminator decides whether the image is real or fake. Now let's go into the architecture. Initially, a low resolution image is given as the input, and then later it's passed to the convolution parametric ReLU functions. And here, this one block is a residual block. There are 16 such residual blocks, and each one of them contain a convolution layer, a batch normalization, a parametric ReLU function. Now this later in the later end of the network, we see there are pixel shufflers which upsample the image and produce super resolution images. Now, this is given along with a high resolution image to the discriminator network, which again passes through convolution layer leaky ReLU function. And then lastly, we come to see that it passes through a sigmoid activation function in the end of the network, which then identifies whether the image is real or fake.
Coming to the loss functions. Now, traditionally in the super resolution for super resolution tasks, MSE loss is used. MSE loss does a pixel to pixel comparison between the high resolution image and the super resolution image. Now, MSE loss it produces overly smooth images and also lacks high frequency details in the super resolution image. These are some of the drawbacks in MSE loss. Now, the loss function that we use in our project here is the perceptual loss. The perceptual loss is basically just a weighted sum of a content loss and an adversarial loss. So content loss is basically a feature space MSE loss, which is calculated by passing both the high resolution image and the super resolution image into a pre-trained VGG network. The feature representations obtained at the end of the network are then used to calculate a Euclidean distance between them, and this serves as the content loss for in our case. Now coming to the data set which we used in our project was the DRIP2K dataset, which consists of high resolution images. It consists of 800 training images of 1024 cross 1024 resolution. low resolution images in our project are obtained by downsampling the high resolution images by different techniques. Now, how we go beyond the existing work that is done in this area is we do a breakdown analysis of SR GANs. So basically, we test how SR GANs perform at different downsampling levels and see how the performance varies. Also, we do a comparison between the SR GANs and the SR ResNets. Uh, Also, we test the robustness of training a mixed bag model on various downsampling techniques.
So let's see the breakdown analysis of SR GANs. So this is the example for 16x upsampling. So I just want to give you an idea of how much 16x upsampling is. 256 pixels in the high resolution image is brought down to 1 pixel in the low resolution image. So there's a lot of information loss when it comes to 16x upsampling. Let's look at the low resolution image here. We can see that the zoomed in version, the edges are not that sharp, and it has a very blocky structure. But then when we see the generated image, the edges are much better and they're sharper. Let's look at another example. These are pictures of strawberries, and when we zoom into one particular strawberry, we see the low resolution image has very blurry and blocky structure, and there's not much detail. But then when we look at the generated image, we see that there are pores in the strawberries that can be clearly seen. So the generator is actually doing a pretty good job at it. This is the example of 8x upsampling. This is an example of a 4x upsampling. So now finally we come to 2x upsampling, where we see that the generated image is very much close to the high resolution image itself. So I'm pretty sure if you're the discriminator, you'll have a pretty hard time trying to identify which is the generated image and which is the high resolution image.
Now, moving on to the comparison between SR ResNets and SR GANs. So in the 16x downsampling case, you can clearly see that the SR ResNets perform better than the SR GANs. So they have higher PSNRs, and also the images have better edge definition and also are better looking than the SR GANs. Now, coming to the 8x case, you can see if I zoom into a part of the dog's fur, you can clearly see here that the SR ResNet produces more smoother outputs as compared to that of the SR GAN. The SR GAN, you can see that the dog's hair has higher definition. You can clearly spot the hair, and you can see that it's more realistic looking. Now, these are the images for the 4x and the 2x cases. You can see that the SR GANs always have a lower PSNR than the SR ResNet, but the images are more realistic looking.
Next, we come to the mixed bag SR GANs. So in the real world, you just don't see one type of low resolution image. We see a low resolution image that is a combination of different downsampling techniques. So we trained a model on 4 different downsampling techniques, so namely bilinear, bicubic, nearest neighbor, and the lang source. We see that the generator is able to produce good images, comparable images, when we gave in bicubic and the lang source as an input image. Um, Next, some of the challenges that we faced were the generator is producing a lot of artifacts during the training process. Here we see that there are black spots that appear in some of the images, and in other images, generator is not able to capture the background of the image. Also, GANs take too long to train. So our GAN actually took 7.5 hours to train for 30,000 epochs on Tesla V100 GPU.
In this video, we discussed in a lot of details about this super resolution using GANs. We discussed the capability of SR GANs in terms of how much upscaling it can effectively achieve. We discussed, we compared the output of SR GAN with conventional CNN-based SR ResNet, and we also discussed how using different downsampling techniques to train the SR GAN can affect its output. And going further from here, there could be a couple of interesting directions to pursue. One of the very interesting things to see would be how the output image quality is affected as we reduce the network size. Small network sizes could be of interest for low latency and low power operations, but at the same time, we also want to maintain output image quality. Another thing to see could be incorporating MSE loss, or somehow combining straightforward upscaled images with the GAN output in the network. This way we can perhaps make the network learn to color those low frequency patches really fast, and maybe even avoid these artifacts.